Swayam Prabha. Digital India. Educated India.
Right? Then how to estimate the sediment? This is very important because there are certain reservoirs in the world which got filled up at the first fill up itself because of improper sediment estimation. This reservoir sedimentation, there are two types of sediments. One is bed load, that means huge boulders which are rolled by the water and bringing it at the site, like rolling, sliding, hopping. These are all the different ways on which the bed load is transferring from one location to another location. The second one is suspended sediment, SSL. Sometimes coarse medium sediment to fine sediments will come as the suspended sediment. When there is a flood water, it will carry even the medium coarse and suspended sediments, right? That's why it's a different brownish, light brownish color, right? That is nothing but water flowing with sediments. So I have to estimate this bed load separately and suspended sediment load separately. There are several empirical formulas available to estimate this bed load and suspended load. We will see that separately, right? Thus, as I said, the sediment load consists of two categories: suspended load and bed load. The suspended load, which remains in suspense, generally fine sediments and carried away by the river to the delta. Right? The suspended load in the stream is measured by sampling. Right? Take 1 liter of water, filter it, find out what is the sediment trapped in that, and then weight of the sediment to weight of the sediment and water. It's a percentage in ppm. The data on suspended load measurement and corresponding stream discharge is called as sediment rating curve. If it is sediment simple rating curve, we call it is a relationship between discharge and a stage. Okay, but here it is relationship between discharge and sediment, and that is why it is called as sediment rating curve. The correlation between the sediment load and the discharge, right? Normally it is plotted in a logarithmic paper to find out what could be the sediment when the discharge is larger and larger at a site. The bed load. Now we will see one by one. The bed load are the particle which is moving on or near the bed. This depends upon the velocity of flow, which makes the sediments to roll, slide and pop. There are certain analytical methods, right? First method was Du Bois, right? It's a sand moves in layer subject to uniform tractive force, right? Where this depends upon the shear stress as well as the bed load rate of transportation, right? Per load per second per unit weight. It depends upon the shape and size of the sediments, CS, as well as the shear stress of the channel boundary. If the channel boundary is very smooth, then my sediment rate will be larger. If my average shear stress is very large and critical is also very large, then there will be a less tractive force. So more tractive force, so the sediment may not roll. Right? Then we have Shield's formula, right? That also depends upon the specific gravity as well as the shear stress of the bed material. Right? Just to show you that the sediment load is estimated mainly based upon the shear stress of the channel boundary, critical stress, as well as shape and size of the sediments, as well as specific gravity. Right? No need to remember all this formula, but remember that what are all the parameters used to estimate this sediment load. Then sediment deposited in the reservoir. All the sediments carried by the river gets deposited. The large suspended bed materials, they get deposited at the mouth of the reservoir, I told you. So this is the dam. When we stop it, because of reduction in velocity of the flow, the huge coarse sediments gets deposited at mouth of the dam, and that is also called as delta. Not only at the downstream side you have delta, the upstream side in the dam also you have this. delta, right? So that is called as delta at the beginning of the reservoir. Smaller particles remains in suspension for longer period, and because of their high density than the water. Then what happens? They settle when the water stored is for longer and longer period. They used to settle at the dead storage area, that is fine sediments. Okay, these are all the sediment. These are all the zones of sediment deposition, right? Coarse, medium sediments and fine sediments will be floating, and then which will go. Then the sediment deposition is almost called three types. First one is top set. Top set is nothing but my delta, which is larger size sediment and extended up to the backwater curves, right? The second one is foreset. Foreset is nothing but the face of the delta where my medium size sediments gets deposited. It is the transition zone having steeper slopes and decreasing in grain size. Bottom set is nothing but fine sediments that deposits at very low quantity in the dead storage. Right? So knowledge of sediment deposition is essential for designing this reservoir dead storage volume, right? Because there are several factors which governs this distribution, and one important factor is, you can see that in earlier figures we said that this is the dead storage and then live storage and flood storage. If you see here, the sediments are getting deposited in the live storage area. When the sediments are getting deposited in the live storage area, my live storage goes on reducing over the period of time. So dam is there, but after 50 years or 60 years, my entire live storage will be filled with dead store, with sediments. That means the volume of water available for my usage goes on reducing with increase in sediment deposition in the reservoir. That's why reservoir estimation is very important. But these are all the factors which governs the places where the sediments gets deposited, also called as distribution pattern of the sediments. It depends upon the slope of the river, length of the river, constriction in reservoir, size of the sediment, capacity inflow ratio, reservoir operation. If I do frequent operations, they used to get rolled. If I am not doing frequent operations, then all sediments gets deposited. Then vegetal growth in the water spread area, river inflow pattern. If it is daily flowing, sediments will be less. But if it is flowing only during monsoon period, sediment will be more. Then sediment load. In India, Himalayan range reservoirs will have more sediment than our Deccan and southern dams, because the erosion at the Himalayan range is larger. Then shape of the reservoir also governs how these sediments are deposited. Then outlets, what type of outlets, how the outlets are operated. These are all the ratio, these are all the patterns which governs the distribution pattern. Out of all these things, I have classified this into three characteristics that called it as the factors influencing the rate of sedimentation. Rate of sedimentation is nothing but what is the rate at which the sediments get deposited in the reservoir. This is three characteristics governs. The first one is the catchment characteristics, second one is the reservoir characteristics, and third is the sediment characteristics. Suppose if we will see one by one. Watershed characteristics. What is the watershed characteristics? Not the physiographic features, it is the land use and land cover. If it is with high density forest covered, then the impact of rain on the soil is very less. So it is very less eroded. Okay. If it is a barren land, there will be more erosion. The second one is the type of soil. If it is an erodible soil, even light rainfall can erode more quantity of soil and bring sediment to the reservoir. Second one is a good forest area, but the forest area is steep slope and it is subjected to landslides. Then sediments will also be more. So watershed characteristics also governs the rate of sedimentation. The second one is the reservoir characteristics. Reservoir characteristics is nothing but how I am operating the reservoir and the sediment content which is coming into the reservoir. Then the third is the ratio of capacity and inflow. Suppose if the capacity of the reservoir is more than the inflow, average inflow at the dam side, that means you are trapping almost all the water coming into the dam. Then what happens? You are trapping more and more sediments. So then that is called as trapping efficiency of a reservoir. How much sediment is incoming into the dam and how much is outgoing? Then what is the ratio of sediments that are trapped? That is called as trapping efficiency of a reservoir. We will see that in detail. Then the last characteristics which governs the rate of sediment is sediment characteristics. That like sediment size, texture, shape. Suppose if the sediment size is very large, then they get deposited at the mouth of the reservoir itself. Suppose if the sediments are always in coagulant form, then whenever we open the gate, it goes away, right? So these are all the characteristics which governs the rate of sedimentation. Now let us take this trap efficiency, which is one of the most important governing parameter in estimating the volume of sediment deposited. What is this trap efficiency? Trap efficiency is the proportion of the incoming sediment that is deposited or trapped in a reservoir and is often expressed as the percentage, like T is Vi minus Vo by Vi. That is volume of inflowing sediment load to the volume of outflowing sediment load. How do they do this? We have to estimate what is the sediment incoming and sediment outgoing through the canals. Sometimes it may not be possible to measure everything. Then we used to estimate this trap efficiency, and there are several methods available to estimate this trap efficiency, because this trap efficiency depends on several parameters like sediment size, its distribution, like what you do in geotechnical engineering, soil size distribution, right, using sieve analysis. Then the time and rate of water inflow into the reservoir shape and size, location of the outlet structure, and water discharge schedules. CE401 Water Resource Engineering, we are seeing one of the important water resources creation, that is dams and reservoirs. In that we are looking how to estimate the sediment dead storage level, which is based on the trap efficiency of this one. This trap efficiency is also estimated every time, every year for large dams, so as to estimate how much is the volume of water reduced due to sedimentation. That is why these trap efficiency studies are very much important nowadays in water resource management. This trap efficiency, as we see, it's ratio between the incoming sediment to outgoing to the incoming sediments, or how much trapped sediments are getting deposited in the reservoir. When it's not possible to measure and estimate, we do the estimation. So while doing the estimation, the characteristics which governs this trap efficiency process are majority two. One is the settling velocity of sediment particles and retention time. Right? The settling velocity are incoming sediment characteristics, whereas the retention time is the reservoir operating characteristics. For example, we will see one by one. Settling velocity, incoming sediment characteristics which governs this is the particle size distribution of the settling velocity, flocculation control. These two governs the settling velocity. The retention time is again divided into two important characteristics. One is the inflow characteristics and pond characteristics. The inflow characteristics which governs this is the runoff volume, peak discharge and base flow. Whereas pond characteristics, which is nothing but how this reservoir is operated, like reservoir topology, either it is a dry pond or semi-dry or permanently ponded, what is the surface area, storage area relation, shape, outlet dimension, outlet type, right? Then location of the outlet, initial storage volume, the property of the bottom of the surface, vegetated, non-vegetated, stiffness and the height of the vegetation. So this trap efficiency estimation was the subject of the study from 19 30s and 35s after formation of large reservoirs. Why it is very useful? Because this trap efficiency is useful to estimate the life of the reservoir. It is not the structural life, the hydrological life, right? So what is hydrological life? We can divide that into different life. That means whether the stored water can be economically usable, right? So that is why people call it as useful life. Useful life is nothing but the period in years during which the sediment deposit does not affect the intended primary use of the reservoir, right? That means the dead storage is sufficiently designed so the sediments are not seen in the outflow of the dam, like either it's for irrigation or power production or drinking water, drinking water purpose. And the end of this useful life is when the basic minimum capacity falls below the dead storage, right? And then it will fail to meet the minimum basic demand. Until that period is called as useful life. Then usable life is the reservoir can continue to serve. See, still it has come only up to the dead storage, but still I can draw the water and use it after treatment. So such period is also included in the use life and it is called as usable life. The reservoir can continue to serve some of the purposes, though to limited extent, even after expiry of its economic life. Okay, so that is called as useful and usable life. Economic life is the point of time at which the effect of various factors of this depreciation of sediments, change requirements, time discontinued alone for risk, uncertainty. That means it is that the amount of money earned by supplying the pure water is becoming uneconomic. Then that is called as uneconomical life. Decent life is each and every storage is fixed, assuming 100 years, 50 years. That's the dead storage volume. Suppose if the volume of the dead storage, volume of sediment deposited is more than the dead storage, we say that it has reached the design life. Full life is the number of the years required such that the reservoir is completely filled with sediments, which may not be, that means no water can store in the reservoir, right? So there are different steps in estimating the useful life of reservoirs. One of our research carried out on this is three different steps we carried out. First one is to estimate the sediment yield from the catchment area. Right? When I want to study the volume of sediment eroded from the catchment area, I need the aerial data of that catchment. If I want the aerial data, then I need to go for a remote sensing map. So then use remote sensing and GIS environment, estimate the erodible catchment area. So that will help us in spatiotemporal amount of sediment incoming to the dam, right? So this FISAC model is very important model, right? Which will help us to estimate how much sediment can be expected for different rainfall intensities of the given catchment. Then the second one is estimate the trap efficiency of the reservoir, because some X quantity is coming, how much of this X quantity is trapped in the reservoir. If all the X quantity is trapped, then you can easily estimate what is the economic life or usable life of a reservoir. Sometimes for large reservoir, it is almost 99.99% all sediments gets deposited. There are conventional empirical methods. Then we modified such conventional methods developed in other countries to suit to our Indian reservoirs. Then now people used to estimate or measure this trap efficiency. How they measure? They will measure the volume of water stored at every year, not just estimating from the area elevation storage curve. They will do the sounding depth in radial direction from the dam face throughout the dam. Then there will be a change in the contour level because of sediment deposited. That means you have to redraw actually the contour maps, area elevation curve. Then the difference between previous area elevation curve, and current area elevation curve will give you the reduction in volume of water stored because of sediments. From that also people used to estimate the trap efficiency. Once I have this measured volume of water for different levels for longer period, or volume of sediment deposited is measured for longer period, then we can apply our data driven techniques to estimate this trap efficiency. Then the third step is to estimate the volume of sediment retained, and then from that we can estimate what is the useful life of a reservoir. I will give you some of the conventional model, right? This conventional model, RS is the annual mean silt deposited, is a function of C by I. Almost all empirical formulae or depends upon this ratio of capacity in flow. Right? Just remember which is the most important parameter which governs this trap efficiency. Not only in east part of the country, western part also several people have developed this trap efficiency estimation. Okay, like Taylor's method. Gill's approach is the most important method widely used throughout even today now by different dam authorities to estimate what is the reduction in the capacity of the reservoir for a given time period delta T after estimating the trap efficiency, right? So it is function of the reduction in the volume of water stored is function of the annual characteristic weight, specific gravity, trap efficiency, and time period and specific weight of the sediment deposited. Now we have modified this to suit our Indian condition, and we estimate this. These are all different characteristics, different trap efficiency or useful life given by Gill for different types of sediments. If the dam is having coarse, what is the useful life? If it is having medium sediments, what is the useful life? If it is having colloidal, what is the useful life? And finally, we also incorporated certain characteristics to estimate this. It's called Gill's method. Right? The main idea here is to prevent this sedimentation. Why we need to estimate? It's a threatening figure. 90%, 99.9% of the dam sediments incoming are trapped. That means every year we are losing certain amount of volume where water used to store to sediment. So water cannot store. So my capacity of the dam goes on reducing. So I need to prevent that sediment incoming into the dam. Right? So some of the methods are catchment development authorities, thereby reducing the control by constructing check dams, gully dams, contour bunding, trenching, agronomical forestation, right, vegetation growth. These are all some of the methods to prevent this reservoir incoming sediments. Like in stream measures, we can do check dams and diversion dams. Or while planning the reservoir, you can plan such that the watershed area doesn't have area prone to landsliding or soil erosion. Then construct the reservoir away from the stream which is having large amount of sediments. Then while designing the reservoir, depending upon the measured sediment for a certain period, provide the appropriate area or volume for the sediment deposition. Then design an appropriate outlet such that the sediments will get flushed off. Very recent technique, this one for outlet work, is the orifice spillway type. Earlier, the surplus water used to go above the dam. Nowadays, people are designing the orifice spillway. That means the flood and sediments gets discharged from bottom of the dam, so that the outlet will work as a dual purpose. One is for flushing the sediment as well as for releasing the surplus water. Okay. So then dam rising in stages, instead of rising the dam continuously, you do stage by stage, thereby you are creating the obstacles for the sediments coming in. Then reservoir operation, you have to control the sediments by appropriate operation. Don't keep the water for longer period. Then every sediments gets deposited. Then give way for the peak flood so that the coagulant sediments will go away from the reservoir. These are all some of the curative measures. Curative measure means, so by all this means sediments is still depositing, then manual excavation, dredging, right? These are all, or sluicing with hydraulic and mechanical agitations. These are all some of the curative measures to remove the silt deposited in a reservoir, right? So these are all some of the self-studies, all water resources words related to dam, weir, barrage, reservoir and sediment, and also related words like planning, designing, construction, operation, management of these dam reservoirs. So dear friends, we will wind up here about this reservoir engineering.